All right. Before we start today's class, I still hope you can refresh your mind about the operation conditions for the MOSFET, especially in saturation region. So you can see this diode connected MOS. For this one, actually, the gate and the drain have the same voltage. It means VGS equals 0. To make it on, VG needs to be VTH higher than VG. Okay, so you promise this through such kind of diode connection, drain should always be off. I mean pinch off. Okay, then it depends on how much current you flow through such kind of diode connected transistor. If it is on, then it should be in strong inversion, in saturation region. That is what I mean. It never be in trial region, because in trial region, here and there should be on at the same time. Okay, and then you need to also keep memorize that what is the requirement for the operation voltage? Yeah, VG needs to be VTH plus delta VDSS or something. Okay, yeah, so not only VTH higher, but with some kind of voltage difference to support the operation in saturation region. But how much is such kind of delta VDSS? Yeah, you can see that. Finally, according to such kind of very simple mathematical derivations, you will get delta V. In brief, okay, yeah, should be proportional to the square root of L over W. It means what? The wider, the less delta V. It means it is more conductive. Okay, yeah, but the longer, the larger delta V, because it is less conductive to support the same current. This is what I need to point out, that usually we suppose that the bias current is fixed during your fine tune. Okay, if you would like to change your WL, usually the condition is the bias current is fixed. Okay, then you will see such kind of very important idea. Please memorize it, because it's very easy to memorize. Okay, very easy to remember it. So you can see delta V again proportional to the square root of L over W. Yeah, the longer, the larger delta V. That is, yeah, what I would like to tell you. This is for MOS. And how about PMOS? Do it for yourself. Okay, with almost exactly the same reasoning, you will see the operation principle, the conditions for PMOS. Yeah, and then how to estimate the minimum voltage for such kind of saturated MOSFET under operation. Again, I would like to focus only on MOS and explain by yourself for PMOS. Yeah, so MOS here, okay. I told you already, for MOS, yeah, here and there should be one VTH and one delta V higher. Okay, it means what? The source needs to be one delta V, one VTH, one delta V lower than gate and drain, because the gate and drain are connected. That is the diode connection. A similar condition for PMOS. So it means what? The source, sorry, this is the source, okay? The source is one VT, one delta V higher than your gate and your drain. Yeah, reversely, your gate and drain should be one VT and one delta V lower than your source. I mean for PMOS. And how about the non-diode connected MOSFET? Yeah, you can see what is the condition to make it operate at saturation. Yeah, we remind you again and again, gate to source needs to be on. gate to drain needs to be pinched off. Okay. So this condition, again, the gate should be 1 VT, 1 delta V higher than your source. Okay. And then how to make the drain still pinch off? Yeah. So reversely, on the contrary, how to make it on? The drain needs to be 1 VTH lower than the gate, right? Then it will be on. But if both here are on, they are on, then the MOS operates in trial region. Okay. So how to make it off? Oh, very easy. Yeah. The drain needs to be at least 1 VG minus 1 VTH or higher. That's it. Okay. So what is the minimum voltage the drain can have to make the MOSFET operate in saturation region? It cannot be 1 VTH lower than your gate. Okay. It cannot be. So the minimum is 1 VTH lower. That's it. But according to source, here gates are 1 VTH and 1 delta V higher. But you can bid 1 VTH lower than the gate. So the delta V, the drain voltage can be, the minimum drain voltage can be delta V higher than your source. Source again is the reference point. Okay, that's it. Piece of cake. Okay, so again, if you look at here, your gate should be 1 VTH and 1 delta V higher. But how about your drain? The minimum voltage is delta V, okay, or higher, to make here on, there, pinch off. That's it. And how about the PMOS? The same, yeah, with similar reasoning. You will see the gate should be 1 VTP, okay, and 1 delta V lower than your source. And how about the drain? Again, with similar condition, yeah, 1 delta V lower. Okay, that's it. All right. But I would still like you to pay much more attention to here. Yeah. Again, your drain voltage for MOS can be 1 VTH lower. Okay, to make here still pinch off than the gate. Not only exactly the same, but you can go lower until 1 VTH. MOS will still operate in saturation region. That is the good news for everybody. Okay, in this way, we can get more the so-called output swing. Output swing will be larger for the drain. Okay, it can be lower. And how about how much higher? Oh, in theory, yeah, no limit. But in practice, until the drain gets into breakdown region, okay, usually more than 10 volts for mature processes. For new processes, I think a few volts at least. Okay. Yeah, but for new process, the VDD usually is only 1 volt or even less, right? So a few volts means very large. So you don't need to, for your regular design, you don't need to worry too much about the breakdown operation for your drain. Okay, forget about it. Usually you don't face such kind of difficulty. And again, how about PMOS? The drain can be 1 VTH higher than the gate. Okay, please keep this in mind. That is very important. So for NMOS, the drain can be 1 VTH lower than the gate. For PMOS, the drain can be 1 VTH higher back to your VDD. Okay, and this down to your ground. Yeah, both can expand your output swing. Okay, with such kind of, well, I think I taught this already, right? Right? Already, right? Okay. Then, yeah. Oh, so why? for the video recording, yeah, it seems that we only talked about the operation region. But to my memory, I talked about this negative feedback, right? What is the most important slogan for negative feedback? You can sacrifice your gain, okay? Yeah, how can I say? You can trade your gain with all the other parameters. For example, if you reduce your gain by 100 times, then almost all the other parameters will be enhanced by exactly the same, almost the same amount. For example, your bandwidth will be enhanced by 100 times. Your linearity will be enhanced by 100 times. Your error will be reduced by 100. Okay, yeah. So only if the gain is high enough, you can reduce your gain. I mean, through negative feedback, to improve almost all the other parameters. That is a very good idea, very important idea for analog IC design. So we apply negative feedback again and again. Yeah, that's it. But for this, without any derivation, as I mentioned already, if there is no such kind of negative feedback, how about the cascade, the output resistance for cascading? Yeah, we know that is your own, the load here is RO2, right? Will be enhanced by your own. What is U? I mean the cascading transistor. Okay, your own transconductance and your own output resistance. Okay, GMRO usually means 100. Two-order increase in such kind of output resistance, and then we apply such kind of negative feedback. But I explained already, the major purpose is to keep your I out as stable as possible. It means what? All the negative gain applied here will be sacrificed to make your AI, exactly the same as 1. So all the negative gain here will be sacrificed. So what does it mean? And for all the other parameters, including your output resistance, will be enhanced. But you need to be very careful. Enhanced according to your need, up to your need. Okay. If you would like to make the output resistance higher, then it will become higher. If it needs to be lower, then it will be reduced by such kind of amount. Okay. According to my slogan, my estimation, only AV, because AV totally sacrificed to enhance all the other parameters. That is for estimation. And how about derivation? The only difference is 1 plus AV. Okay? 1 plus AV or AV. Actually, it doesn't matter anymore. Yeah. Why? Because even you get this, it's still far away from truth. Okay? Yeah. It never be really accurate. For accuracy, you will say, hey, for such kind of derivation and your simulation, which one is more accurate? Derivation is much more. Simulation is much more accurate than such kind of simple derivation, because I told you already. For humankind, you can only focus on such kind of linearized models. Okay, only if the models are linear, you can derive something. If it is nonlinear, I promise you, with almost 0%, you can derive anything, nothing. Okay, so from the very beginning, derivation is incorrect because, first of all, it needs to be modeled and linearized. For modeling, for linearization, you will get a lot of error. So forget about it. Inaccuracy. Okay? So derivation is the least, because by the nature, from the very beginning, it is not accurate at all through modeling and linearization. No. All right. So simulation. Oh, for simulation, it will be more nonlinear, but by nature, it still have such kind of we call piecewise linear. It is not real nonlinear, but it tries its very best to apply such kind of piecewise linear to approximate nonlinear behavior. But it still be much more accurate than such kind of derivation. So forget about this. Okay, I myself will be much happy with such kind of estimation, because estimation derivation, both of them are not accurate at all. Even simulation is not accurate. Okay, it still gets such kind of modeling from TSMC, UMC. With modeling, it means it never will be true. All right. As an engineer, don't pursue accurate result. Okay, you need to tolerate inaccuracy. I mean, you need to tolerate error. If you would like to reduce the error to 0, please don't join us. You can be some kind of mathematicians, but even you cannot be any kind of physicians. Okay, for physicians, they still need to tolerate some kind of measurement error. Only for mathematics, you can get exactly solution without any error. How about engineers? We need to tolerate much more error than physicians. Never mention about anything related to mathematics. Okay, so it never be true. To myself, 1 plus AV and AV are the same. They are all wrong. No, they are all inaccurate. Okay, but with such kind of estimation, you don't need to derive anything. Only if you have very good logic thinking, intuition, configurations, within seconds, you can estimate how large the result will be. Okay, it will be very time saving for your own IC design. Yeah, anyway, we can go further for Wilson current source, the same, you have such kind of cascading, so the R look like this. Okay, again, yeah, but what is the problem here? The current ratio won't be accurate. Yeah, because for 1 to 1, if M1 and M2 are exactly the same, we hope the output current will be exactly the same as the input. That is the accuracy for current ratio, right? But here, the structure promise you no accuracy for your output current at all. Again, which transistors control the current accuracy? Which transistors? You need to remind yourself again. What are the critical devices? M1 and M2. Okay, they control the current ratio. And how about M3 or even M4 here? They are only cascading. They help us to increase the output resistance. That's it. For cascading transistor, I told you already, they behave just like a current buffer. Okay, what's the matter? Too dangerous. All right, anyway, here M1 and M2 doesn't operate at the same condition. Why? Because VDS1 here, VDS2 there. According to saturation region, the voltage here needs to be 1 VTH and 1 delta V lower, right? So channel length modulation will make M2, the output current of M2, less than I reference. And M3 is again a current buffer. It means what? The current here will flow through M3 100% to the output. That's it. IO will equal to IDS2. And here, it doesn't flow anything. Okay? So, yeah, my current exactly the same as you, but my current is less than M1. That's it. Okay? So, for such kind of precision, high precision ratio is not obtainable. It means IO is imprecise according to the transistor ratio. How do you improve it? Here. Okay. So this is sometimes you call it modified Wilson current source. Yeah. We need to introduce one extra M4. For what? See? With the help of M4, the drain voltage here will be, again, this is MOS, that is also MOS, right? So my voltage need to be here and 1 VTH and 1 delta V lower. Exactly the same as there, right? So the major help from M4 is to make the drain voltage of M1 exactly the same as the drain voltage of M2. That's it. To balance the conditions for both M1 and M2. Again, who controls the current? Those two. Those two. To be a very good analog IC designers, you need to know exactly who are important, who are not. Okay, I'm talking about which devices are critical, which are not. You need to train yourself. All right, so which are important? M1 and M2. Yeah, and according to M3 and M4, yeah, if you have time, you can match them. If you don't have time, you don't have chip area, right? The chip area is not large enough, then forget about M3 and M4. Critical devices are here. You need to make M1 and M2 hopefully about the same with many kind of layout topology or even with calibration. For what? To make I/O hopefully about the same. I cannot say exactly the same, never. Okay, about the same as I reference. If you don't do anything, I promise you, at least, yeah, one order in percentage for mismatch. That is what we need to face in the future. Okay, yeah. Because hey, we are engineers. We need to tolerate inaccuracy, right? But not so large. Okay. Usually, we need to tolerate how much inaccuracy we need to tolerate according to your application. For example, 8-bit ADCO tech and 12-bit ADCO tech. This one, the tolerance is much smaller than that one. Again, up to your application. You say, hey, I'm so talented. I can make the error to 0. Congratulations. You can design infinite bit of data converters. Forget about it. Yeah, nothing like this exists on Earth. Okay, we are humankind. We are not gods. Forget about it. Yeah, again, for such kind of modified Wilson current source, you can see precise ratio. Okay, because if M1 and M2 are exactly the same, that is the assumption. Okay, under such kind of assumption, if both operate at the same conditions, you can see the gate voltage are the same, the source voltage are the same, and how about the drain voltage? I told you already, because 1 VTH lower, 1 VTH, 1 delta V lower, 1 VTH, 1 delta V lower. Congratulations, because for M3 and M4, the gate voltage are the same, right? So 1 VTH, 1 delta V lower, 1 VTH, 1 delta V lower. Congratulations, but you still need to promise me M3 and M4 should be exactly the same. Otherwise, they don't have the same VTH. They won't have the same delta V, okay? Okay. It still has some kind of minor effect, Yeah, instead of no effect, no. So I'm telling you, M1 and M2 are critical. And how about M3 and M4? They are not so critical, but they still have some kind of impact on your output. Okay? Yeah, then go further. But what is the problem here? They say, hey, it looks very good, right? M1 and M2 can, yeah, we balance the condition for M1 and M2 so that current ratio can be accurate enough. And again, we have cascading to make output resistance much higher than before, right? What you can expect, even more. Anyway, there's some problem. The output swing or the headroom, tailroom, I tell you already. For ideal current source, it looks like this. But for practical one, it looks like that. This is the headroom. And that is the not large enough output resistance. Okay. How about headroom here? Again, I told you already, for MOS, gate to source needs to be 1 VT plus 1 delta V higher, right? And here is diode connected. So from here to there, another 1 VT, 1 delta V. So you have 2 VT, 2 delta V. And how about the minimum operation voltage for your I out? The drain for MOS, the drain can be 1 VTH lower than the gate. So the minimum operation voltage for such kind of current source is 1 VT plus 2 delta V. Wow. For 0.18 micron, 1 VT usually means 5, 6, or 700 millivolts. And how about delta V? Usually, 200 millivolts or something. So I promise you, the headroom at least 1 volt for 0.18 micron. Okay? 1 volt for 0.18? Does it make any sense? Not much. Why? Because the VDD is only 1.8. That's it. So if you apply, that is some kind of rough estimation, okay? Don't be scared. But anyway, for the output, if you apply cascading for MOS, how about PMOS? If you don't apply, then the R out here, very good. The R out there, not so good. But they are in parallel for AC operation, right? So the smaller, in parallel, it means what? The smaller will dominate the real RO, right? It doesn't make any sense. This is good, that is no good. Then the result is no good because the smaller dominates the result. So what do I mean is usually you need to apply cascading to both sides, to MOS and to PMOS, right? So what is the consequence? Even with 0.18 micron, such kind of very old and mature process, it means what? Cascading here, cascading there, then the operation range will be really, really small. Only a few hundreds of millivolts. 200, 300, no more. Okay? Oh, that is really up there. But I need to warn you. Yeah, I'm only talking about from 0 to VDD 1.8. Yeah, here, no good. There, no good. Only a few hundreds of millivolts here. But if you, when necessary, if you need to operate even a little bit higher, a little bit lower, what is the consequence? You say, hey, it fails. No. It doesn't fail. But the performance will be degraded a little bit. But the further into this region or that region, the more degradation you need to face. Okay? usually that is not some kind of hard border line. Yeah, just like the border between USA and Mexico right now. Donald Trump will like to make it a hard border, yeah, to prevent anybody to get in. But anyway, nothing happens in nature. This is never be any kind of hard border. You can still penetrate into the other side. But I promise you, I warn you already, here the performance is the best. But when you penetrate into the other side, the deeper, the more degradation you need to face. That's it. So what I'm talking about, usually RO will be reduced. The deeper, the more reduction in your actual out. Okay? But how further you can get in, it is up to your application. For some application, it's okay. For the other application, it's not so good. Okay. Anyway, again, as a teacher, I cannot tell you, oh, they are hard borders. You cannot cross over. No. Nothing in the nature behave like that. Okay. Anyway, if you would like to make the headroom as small as possible, okay, I mean, if you would like to make the headroom or tail room the smallest, the minimum, what we can do? Okay, here. If this is for output, I told you already, in theory, okay, that is very important. In theory, for animals to operate in saturation, they need to operate in saturation usually. Yeah, to realize any kind of function, all those functions for you. Usually, I mean usually. For some very special cases, yeah, we would like them to operate maybe in trial region or even in weak inversion. Okay, yeah, anyway. But usually, those transistors need to operate in saturation region. So during your simulation, yeah, the Q point from the very beginning, SPICE or HSPICE, they will help you to analyze the DC conditions, the DC operation conditions for all of you. You can check the condition for each transistor. Saturation, trial, or even off. Sorry, usually your circuit is incorrect. Okay, you need to modify the bias, the width or the length. Okay, that is the usual case, but not always, only the usual case. Anyway, for output current, this is some kind of current source. We hope RO should be very large. To get large enough output resistance, all those need to operate in saturation region. If not, RO will be reduced substantially. That is the consequence. So according to my previous slides, I told you already, for animals, in theory, to operate in saturation region, the minimum voltage for the drain is only delta V, right? And according to Cascodian, for M2 and other delta V, in theory, to make M2 operate in saturation region. That's it. So what is the minimum operation voltage for your I out? In theory, 2 delta V. Okay? Wow, very easy, very simple. It is much less than what I told you here. How much? 1 VT plus 2 delta V, right? Wow, we can reduce the minimum voltage by 1 VT. 1 VT means very much, okay? Very large. But how to make it? So, again, I will show you the power of rough estimation. Delta V here, delta V there. I don't calculate, I don't derive anything, only by estimation. And then, but how to make it true? You need to see, here are delta V, right? But how about the gate? The gate needs to be 1 VT higher. So this should be 1 VT plus 1 delta V, right? And how about there? Similarly, from the source to the gate, it needs to be 1 VT, 1 delta V higher. Okay? Or you can say, hey, you are not happy, you say, hey, how about from the drain to the gate? The same, 1 VT higher. So you get exactly the same, right? From here. Perfect. Okay? Delta V. Another delta V, so it means 2 delta V here, right? So from drain to gate, 1 VT higher. We say, I'm not happy. How about the source? Oh, from the source to the gate, 1 VT, 1 delta V higher, but the source is already delta V, right? So you still get the same. Haha, congratulations, that's it. Okay? But the problem is, how to make the proper bias voltage for M1 and M2. For M1, piece of cake, because from here to there, congratulations, 1 VT, 1 delta V. That's it. But if you apply it again, you will get 2 VT, 2 delta V. Okay? Yeah. And for 2 VT, 2 delta V for M5, then from gate to source, sorry, you only get 1 VT, 1 delta V, no 2 delta V. And this one won't operate in saturation region. It's no good. So the major problem here right now is how to create 1 VT and 2 delta V for M2. So you need to think, oh, okay, I see. For M5, right? Again, from source to drain, it needs to be 1 VT and 1 delta V higher, right? So you get 2 VT plus 3 delta V. But here, only 1 VT, 1 delta V. The drain and source and the gate are the same. So you have only 1 VT and 1 delta V. How to make it extra 1 VT and 2 delta V? Don't forget what I told you. The VT, okay, here. I told you already. Delta V proportional to the square root of L over W. Okay, under the same bias current. So, what we are talking about, 1 VT, 1 delta V are supposed to be, they are all of the same width and length. That is from the very beginning. Okay, right now, you need 3 delta V. It means what? From here to there, 1 VT plus 2 delta V. How to make 2 delta V? Piece of cake. That is what I require you to memorize, such kind of easy relationship, right? The delta V is proportional to the square root of L over W. Congratulations. How to make 2? How to double delta V? For L. Means good enough. That's it. Piece of cake. Okay? So, here, for all the others, they are all double over L. I mean, that is the first cut. 第一次的猜测. Okay? All of them are exactly the same. But this one should be exceptional because you would like to create such kind of 2 delta V. Okay? For this one, how to double it? I told you already. Piece of cake. Yeah. According to square root, you need to make it 4 times larger than the other. So either you have 4L or you reduce your W by 4. As you like. I don't care. But this is in theory. How about in practice? Not exactly the same. Okay. That is, you can say, hey, I make 4L. Then the delta V will be doubled? No, not exactly. Okay, but for rough estimation, it is correct. Good enough. All right, so here I highlight the aspect ratio for you. W over 4L to make 2 delta V for M4. configurations to make it, right? Yeah, we have 1 VT, 1 delta V, and here 1 VT, 2 delta V. Totally, we have 2 VT, 3 delta V configurations. Piece of cake. All right, that's it. But what is the problem? The problem is body effect. Oh, okay, for such kind of cascoding, we call it high strain, right? Because the output strain can be 1 VT larger than regular cascode. This is traditional regular cascoding. And this is the so-called high strain cascoding. Okay? We have the other high strain cascoding. Later I will show you. Anyway, with the help of this, we make it. But again, that is some kind of forced cut. All right? For such kind of forced cut, the first guess how to make the circuit functional, either through derivation or rough estimation. Yeah, you say, hey, I'm very good at mathematics. I would like to derive. And after that, you get some kind of very so-called very accurate W over L, blah, blah. But after you put all the figures into the transistors, I promise you, it doesn't work. Okay, never mind through derivation or estimation. Such kind of forced cut won't be good enough for your circuit operation. You need to fine-tune the overall aspect ratios. Sometimes you also need to fine-tune your bias current. Anyhow. So after tens of minutes of derivation, you get something not functional, okay, to fit your needs. No, forget about it. And again, this is the power of rough estimation. With estimation, within seconds, you will know how much the sizes of the transistor will be. And again, that is only some kind of first guess, first cut. After that, you still need to have some kind of fine tune for all the transistors. That's it. Okay. And how about the body effect? Oh, it's really troublesome. How to track the body effect? Because I told you already, we put almost all the blame on VTH. Okay. Body effect is one of them. If you have body effect, the body effect of M4 and M2 are not the same, then forget about what will go wrong. Okay, what will go wrong? Here, VTH. My VTH and your VTH are not the same. All right? That is the problem. So you are so picky. You would like to solve all the problems. Then you need to track the body effect of M2 to M4. You need to make them exactly the same. But how to make it? That is another story. Yeah. So body effect of those transistors, they don't track each other. It means they are not exactly the same. Okay. Yeah. Oh, yeah. Anyway. So how to trace, how to cancel such kind of body effects for different transistors? So this is some kind of, again, some kind of rough estimation. How to track if M1 is connected to ground? Forget about it, right? So we would like to track M1's body effect with M2. So how much you need to have for your source? How much voltage? Okay. So after some kind of simulation or calculation, anyway, yeah, I'm not. To be honest, I'm not interested at this. Again, even through such kind of body effect cancellation, you will still see something not so correct for your final circuit. You still need to do fine tune. Okay. So for myself, I will be very happy with such kind of rough estimation for the first gas, and then fine tune the size. Okay, that is the sizes of the bias current. But this is not important at all. I would like to tell you why I still have the slides there. I don't delete the slide simply because I would like to introduce another very good circuit like this. Usually for engineers, when they look at this, they say, look, they are current mirrors. If MA and MB are exactly the same, right? Oh, the current ratio will be the same, right? If they are not the same, for example, here, one here, yeah, my size, my aspect ratio, I mean, is doubled, okay? That's it. Then you will guess, how about the output? You will be 1 to 2, right? Right? But it's really upset that for this circuit, we try to make it the same. They are only 1 to 1. But how? Very easy. With PMOS current source, blah blah blah, something like that. Okay, or current mirrors. I don't care. To make them the same, then what will go wrong? Yeah, because we are 1 to 2, but we generate exactly the same output current in theory, right? So what's going wrong? What's the condition? Okay, again, if both operate in saturation, okay, I need to mention that. How about MA? Because it is diode connected. I told you already, either in saturation or cut off, right? But I don't think you would like MA to cut off. It doesn't make any sense for you. So supposedly, it should operate in saturation. No worries. With such kind of diode connection, because drain is pinched off already, and this should be on, right? So it should be in saturation. Okay. But how about MB? If MB also operates in saturation region, then you will get 1 to 2 output current. It doesn't make any sense because right now both currents are the same. So what does it mean? MB never operate in saturation. Yeah, but again, it cannot operate in cutoff region because it needs to conduct current I, right? So only one choice left. MB should operate in trial region. That's it. Okay. You are in saturation region. I am in trial region. Why? Because I'm larger, supposed to be, right? MB here, MA here, right? So if you operate in saturation, I also operate in saturation. Oh, sorry for that. My current should be 2 times larger than you. But right now, our currents are the same. How does it mean? I need to walk here. I to V, right? I need to walk here, trial region. That is a very simple reasoning. Again, you need to equip yourself with such kind of simple ideas. Okay? Yeah, that is a very good explanation for you. Here and there. No, they are not the same. To make them the same, you are here, I'm there. I need to operate in trial region. That's it. So, logic thinking or reasoning is the most difficult part. After you get the correct idea, then how about the derivation? Piece of cake. Okay? You just apply saturation equations for MA, trial equation for MB, then you will derive. This is the result. Okay? Delta V for B and delta V for A are not exactly the same. For example, if B is doubled from A, then its VDS is 0.3, yeah, of the delta V, okay, for MOSFET A. That's it. And then with such kind of 0.3, this is for you. Okay, for what? How to make 1.2 delta V? Yeah, that is some kind of reference delta V. How to make 1.2 instead of 1 or 2? It is 1.2. Okay, so here I told you, with such kind of structure, saturation here, triode there, yeah, and I'm 2 times than you, right? I can make my delta V only 0.3 of yours. But we need to make it 1.2. What does it mean? It needs to be increased by 4 times, right? How to increase your delta V by 4 times? Again, delta V proportional to L over W. To make it 4, then the length should be 6 times larger. Or the width needs to be 6 times less. That's it. Okay. So you will see here why it is 16. That is the reasoning. Okay, and this is for A. And how about B? B 2 times larger. Okay, so for all the others, derive. No. Estimate by yourself. Okay. I hope I'm a good enough teacher to teach all the important ideas I have. You can copy and paste my logic thinking for your own future. But for such kind of details, you need to handle by yourself. Yeah, if I teach everything in such kind of detail, I cannot finish all the content for you. All right? So we can have a good break here for you guys to think about the ratios. Okay? If you have any question, when I come back, after I get my coffee, after I come back, you can ask any kind of question. But I hope you can discuss with each other why they have such kind of very weird W over L ratios. All right. Let's have a break right now.